Hello everyone, welcome to our PBL Level 1 Physics project. Today we're going to talk about circular motion, but not a regular circular motion. We're going to have a conical circular motion, and we're going to figure out the period of that conical pendulum. And the challenge is, since we're going to use a meter stick, and only a meter stick, to be able to measure the period of that conical pendulum. So that's our investigation, and let's move to the materials. All right, our materials for the experiment is pretty simple. We're going to have our flying pig, or sometimes it's also a cow, so whichever you find. These are working perfectly, so that indeed flies, right? When pigs flies. All right, I think that's the idea behind this selection. And that's one of the material. And of course, this is going to make the circular motion, and then we're going to measure the period of this guy. And we're going to need a meter stick, and that's the only material that students can use to be able to make the measurement of the period. And that's for their experimental value. And for the theoretical value, we're going to need a stopwatch, and that is going to be our theoretical value of the period. So this is going to be the experiment, but how are we going to investigate that? Well, the setup is kind of simple because all we need to do is turn this on and give this a circular motion. It's going to make a circular motion. So, and during that motion, we need to measure some stuff. But to be able to figure out what we need to measure, to be able to find time, we need to do some math. All right, so investigation of this experiment is not going to be straightforward. So you can guide your students for them to be able to find the final result, or you can ask that question, or you can have that investigation as a summative assessment at the end of the chapter. So that's up to you, but that would be a good summative assessment if you are interested. So what is happening? Basically, that is my circular motion. So this is going to be my pig, and it's going to be making that circular motion. So our pig is going to make a circular motion. So that is my circular motion. And this is my string, and its length is L. And this is going to be the radius of that motion. So basically, that is your x-axis. So that is not 2D, that is basically plane. That's parallel to the floor. So, and the best way to start that investigation or that analysis, of course, drawing a Freebody diagram. All right, so if that's not an assessment, you can, if you want to guide them, you can ask them to draw a Freebody diagram. So in the system, we only have two forces. One of them is the weight of our object, which is the mass of the pig and the gravity. And we have a tension on the string. So basically Ft. So these two are the only two forces in our system. And of course, all of our students are having problems with the centripetal force. So they might be adding another force over here, saying that that's a centripetal force because that's a circular motion. But those two are the only two forces in our system. And then when we move to the analysis part of those two forces, what are we going to do? We're going to write our Newton's second law in two axes. So since we have this tension in two axes, one on the x and one on the y, so what should we do? First, we need to resolve that to components. So we're going to have the y component of my tension, and then we're going to have the x component of that tension. And then I'm going to have this mg. And once I write those ft y and ft x, then we get rid of this tension itself. And that's also important. Over here, I have alpha over here. And this alpha is that alpha. And how do I know this? From 0 up, z, and then it goes up. So basically, this is tension coming down, and it's going up. So you have your alpha over here. So from 0, this guy is also alpha. So it's important that this angle and this angle, they're putting that right. And after that, what are we going to do? again, from Newton's second law, all of the forces on the y-axis is equal to mass times acceleration, and all of the forces on the x-axis is equal to mass times acceleration. But this is the part where they need to be careful, and then where they need to comprehend the idea of centripetal force. So this is my only force on that axis, and this guy is the reason for the centripetal force, that circular motion. So that is why this force is going to be my centripetal force, and then this acceleration is going to be my centripetal acceleration. So now I have two equations. So on the y-axis, I have Ty that goes up and mg goes down, so positive and negative, and that is equal to mass times acceleration, Newton's second law. However, this guy, our pig, when we do the demonstration, we'll also see, it is not accelerating up or down. It is only making a circular motion. So that means my acceleration over here is 0. Now we're going to combine those two equations, and let's see what we have. So my y component is equal to, if I take this equation over here and not assume my acceleration is 0, then what's going to happen? Fty, tension on the y-axis, is going to be equal to mass times gravity, weight of the object. And what is Fty in terms of this tension force itself? So since this is the adjacent, this is going to be my cosine. So tension times cosine theta, well, I should have used alpha. Well, not a big deal. So this theta is basically this alpha. All right, so this is cosine alpha, and that is equal to mass times gravity. And if I move to the next equation, Ftx equals mac, then Ftx is equal to centripetal acceleration times mass. So my mass is m, and my centripetal acceleration is that v squared over radius. All right, so then what is my tension on the x-axis? That is your x component, and to be able to find your x component, this Ftx is basically on the opposite side of this angle, then that is going to be Ft times sine theta. All right, so that is my Ftx, Ft sine theta, and that's equal to my mass times centripetal acceleration, so which is mv squared over radius. So now, so far, that's also very difficult for students to do it, because if they haven't taken algebra 2 or pre-cal, I don't know, like where you're like that trigonometry in your curriculum. So if your students are like freshmen or like sophomores, or if they haven't taken algebra 2, they're having a lot of problems over here. So you might need to talk about that sine and cosine idea over here. And now we need to combine those two equations. All right, so how can we combine those two equations? F tension is the same for both of the equations. So then that means I can simplify, or I can solve one of the equations for Ft, and then I can substitute that Ft in the other equation. So over here, that's what I did. So I solved this guy for tension force, and my tension over here is basically mg divided by cosine theta. So mg divided by cosine theta, that is my Ft, and I took this guy and I placed it over here in the second equation. So my Ft over here is basically mg over cosine alpha or theta. So this is basically from the first equation. And Ft is this guy, and times sine theta. This is basically the rest of the second equation, sine theta, and that is equal to m times v squared over r. And now, what do we have over here? mg sine theta divided by cosine theta equals mv squared over r. And again, this is from trigonometry. What is sine theta over cosine theta? That is tangent theta, but I changed it back to alpha, but it's okay. So that's your tangent alpha. All All right, so tangent alpha is equal to what? mv squared over radius. But what I did over here, I canceled those masses first, so you don't have any masses. So you have v squared over r, and I also took that g to the other side. So your tangent alpha became v squared over radius times gravity. So again, this is not over yet. So we just found that tangent alpha equals v squared divided by radius times g. So I need to know the velocity of my pig, and I also need to know the radius that it is rotating around. So I need this radius, and I also need the velocity of this guy. And then we're going to move to the next step. So we know that this guy is making a circular motion. So it is traveling that distance in the time, which is the period. So my velocity is basically defined as distance over time. So what is my distance? Circumference of this circle, which is 2 pi r. And when you divide this by time, that is your velocity. Now what we're going to do the final substitution. We're going to move this v from here as 2 pi r over time into this equation. So we are combining that and that equation together. Now my tangent alpha is going to be what? Well, it changed back to theta again. Tangent alpha or theta, whatever that angle is. So 2 pi r divided by time, because we have v squared. So that is my v squared times 1 over rg, 1 over rg. And now finally what we do is we are solving this equation. I didn't have enough space, so I just skipped one step. So what do? We are solving this whole equation for time t. So because that's what we need. We're trying to figure out my period for the conical pendulum, and I can only use a meter stick. So I am trying to figure out that time. So if you solve this equation for time, your answer is going to be square root of 4 pi r squared times radius divided by tangent alpha times g. So that is my time. As you can see, that's a really long process, and your students are going to have some difficulty to figure out this solution. So make sure that you're giving them enough time and you're giving them enough guidance so that they can come up over here. And of course, the first starting point is a Freebody diagram. Without Freebody diagram, they're not going to be able to come to that conclusion. So now, let's figure out how can we actually figure out my period with just a ruler. So ruler is a meter stick, or is a device that we can measure a distance. So let's see what we have in this equation. I have 4 constant, pi constant, square the pi, that's okay. And I have radius over here. So radius is a distance quantity, so I am going to need to measure that distance then. So I need to find a way to measure the distance from this position, from the center to the final, to the radius, the point that it is rotating around. So I need to find a way to measure that distance from here to here. But I have my tool for that. I just need to figure out a way to measure that distance. Then tangent alpha, or theta. So this is an angle. So how can I measure an angle? So what do? I go back to the equation over here, to the picture over here. My alpha is this one. What is tangent alpha? Tangent alpha is basically opposite divided by adjacent. So I already know this guy, this is r. Alright? So r divided by this guy. And what is going to be the length of this guy? It is going to be, from the Pythagorean theorem, hypotenuse square minus radius square and square root of those two guys. So I need, basically, for me to be able to find tangent alpha, I need r divided by square root of L squared minus R squared. So R is the same R over here, but I have another thing over here. L. What is my L? L is the length of the string. So I need to measure the length of the string as well then. So, and then that means we can figure this one out too, because I need the radius and I need the length of the string. And finally, I need this gravity, and that's a constant too. So as we figured out, we just need to measure the radius and we need to measure the length of my string. All right, so basically a ruler or a meter stick is good enough for me to figure out my time. So that's the analysis. That is how we're going to find, or that's what we need to figure out. And now we're going to go to the investigation part, and we're going to talk about what we're going to do, and we're going to decide how we're going to measure the length and how we're going to measure the radius. All right, so in the equations, we figured that we need the length of the string, and we're going to need the radius, the length of the radius. And meter stick is going to be enough to measure those two lengths. Well, I already make the measurement of the string, and that's kind of easy one. All you need to do is just go all the way top, and that's attached to the string ceiling right now. And then you come down over here, but the important thing for that calculation is you're going to need the distance from the ceiling to the center of mass. So I took this point as my center of mass, so I measured the distance from the ceiling to that point. And that distance is 220 centimeters, or 2.2 meters. All right, and the next thing is measuring the radius. Well, that can be a lot of different ways to measure that. One can be video analysis. You can record a video, and then you can measure the distance from one edge to the other edge, and then you can divide that this by 2, or you can just go from center to the farthest edge, and then you can just measure that as a radius. But what I'm going to do is I am going to use a string, and I'm going to tape that to the bottom, like right under my object. So, and what I'm going to do with that string is I'm going to tape this beginning of this guy right under and make it secure. And then I'm going to let this guy go, and it's going to create a circle. And for this, you need to wait for a while, and then you need to give a little bit like tangential speed at the beginning. So, and after a while, it's going to find its equilibrium rotation. All right. And what I'm going to do is I'm going to go with this string, and I'm going to use my meter stick. So that is going to be my distance from the center. And whenever I'm going to use my meter stick as a reference, so when I'm going to keep this guy away from the pig, and I'm going to bring it as close as I can, and the point that I hit the pig, then that is going to be the measurement. This is going to be my radius, basically. All right, so but I'm going to measure the distance from my center to the string. All right, like I said, there can be a lot of different ways that you can measure the radius, but that's what I'm going to use, and that's actually a good way for you to see how your students are thinking different. And you can, I'm only going to have one measurement, but you can ask your students to, or when you're doing the setup, you can have different lengths of the string, and then you can see how this is changing the pendulum. In earlier investigations, we have seen that the pendulum, over like regular pendulum, simple pendulum, it depends on the length, and that is the only thing that it depends on. So if you have a longer string, then that was taking longer time. So you can also investigate that over here, but since circular motion is way earlier than the simple harmonic motion, that might not be the time that you're going to talk about that, but you can just ask your students to have different lengths, and then you can ask them to compare the times, and then ask them if they can see any like measurable differences. All right, so I'm going to start moving, and I'm going to measure my radius, and let's see what is this. So again, you're going to turn it on. You have on and off button over here, switch, and I'm going to turn it on, and I'm just going to give a little tangential speed, and then I'm going to let it find its equilibrium. All right, right now this string is at the center, and it is attached over here, and I'm going to turn it on, and I'm going to find my radius. All right, this distance so that distance is my radius, because what I did, that was already at the center, and then I waited for this guy. I used my ruler to measure its radius, like whenever it hits to this guy, and that was already measuring the distance from the radius. So whenever I hit that guy, that was the distance that I was holding it. And now I'm going to measure this length of this guy. And let's measure the distance of this guy. So this is 1 meter, and then I'm going to measure that distance as well. And that is 1 meter, and that distance, which is, can say 7. 1 meters and 7 centimeters. So that is my radius. So what I'm going to do right now is I'm going to plug that in to my equation, because I know that this length is 2.2 meters, and now I figured that my radius is 1.07 meters. And I'm just going to plug it into the equation, and I'm going to solve it, and then I'll see what my time is. Now let's go back to our equation, and let's plug in our numbers, and let's see what we have. All right, let's remember our equation. Time, the period for our pendulum was in a square root 4 pi squared r divided by tangent alpha times g. So now we found our radius is 1.07 meters, but that is when the pig hit to the ruler. But whenever you measure, since this should correspond to the center of mass, whenever you measure from the center of mass, you need to exclude the wings, the length of the wings. And whenever I measured the length of the wings, that was 17 centimeters. So my radius is technically 0.9 meters. And the length of the string from ceiling to the center of mass was again 2.2 meters. Now that's my x value, which is square root of L squared minus R squared. So tangent alpha is going to be basically R opposite divided by adjacent, which is square root of L squared minus R squared. So whenever you plug in all of those numbers into the equation, and that's being g, then what you find is 2.81 seconds. So what we're going to do, that is going to be our experimental value. So what we're going to do next is find its theoretical value. And what is going to be the theoretical value? We're just going to let it rotate for 10 times, and we're going to measure the time for 10 times, and then that is going to be our theoretical time value. And let's see what's our theoretical value. we're going to measure the time for 10 oscillation. One, two, three, four, five, six, seven, 8, 9, and 10. Our experimental value, time value, was 281, and we measured the time for 10 oscillation as 2774. So 10t is 27.7 seconds, and what is the time for 1 oscillation then? It is going to be 2.77 seconds. So I'm going to accept this, consider this one as a theoretical value because that's more precise, that's more accurate value than this. So that's going to be my experimental value. Both of them are measured values, but since this is more accurate, I take this as a theoretical value. And then you can do a percentage error. And there's a slight difference. If you think about the difference, it's like 20 milliseconds or less than that. So that is actually a pretty good number. So you can discuss what is the reason for this guy being longer than that. So what can be the difference, or what can be the reason for that? So of course the most important mistakes that kids do is measuring that radius, because that's not easy to measure. And most of the time this L is not being difficult to measure because it's stationary, it's not difficult. But the other thing is the motion is not circular, like it's not perfect circular all the time. There might be a slight swinging when it's making that circular motion. So that is why you're not going to be making like perfect circle. So that is another reason that these two values are not perfectly matching. And the other reason that you can have in the system is, of course, friction. That's always a source for an error. The other reason for an error is the battery. So believe it or not, if you hold it for a longer time, it's not going to take the same time for pig to rotate. So as you run it more and more, it's going to take longer time for it to complete the circle. So make sure that you do not make sure that you do not left it open and then you let it circle all the time. Make sure that you are only using when you are taking measurements. All right. So basically that's our investigation. That was more of a challenge type of experiment. But over here we use a lot of algebra, and then we use one measurement over here. So we measured the two lengths, and at the end we found that the time for the oscillation for a conical pendulum is going to be very similar, and you can find it from just from timing, or by just measuring the radius. By using just a meter stick, you can also figure out the time for the conical pendulum. So that is our investigation, and let's move to our science practices that we have covered in this experiment. What are the science practices that we have covered in this experiment? The first one is students can create representations and models of natural or man-made phenomena and systems in the domain. Well, at the beginning, what we did was drawing a Freebody diagram. So basically, that was the practice that we have covered over here. Next, students can use representation and models to analyze situations or solve problems qualitatively and quantitatively. And furthermore, what we did, by using the Freebody diagram, we were able to drive the equation for time. And we also combine it with the Newton's second law. Next, students can apply mathematical routines to quantities that describe natural phenomena. When we are driving the equation for time, we basically use all of the mathematical steps that we need. So basically that was the practice for that. Next, students can design a plan for collecting data to answer a particular scientific questions. Well, that wasn't too difficult because that was basically the experiment itself, but what we did was after the equation, we figured out we need to measure the radius and we need to measure the length. So they basically, these data were the ones that we need to collect. So students needed to figure out what to measure, but after we derived the equation, that was kind of obvious. But that is the practice that we have over here. Next is, students can collect data to answer a particular scientific questions. So after we measure radius and length, we were trying to figure out the time, the period for a conical pendulum. And our final science practice in this experiment is, students can analyze data to identify patterns or relationships. So students needed to use the correct equations and they needed to use the correct mathematics to be able to find a solution for time, for the period. And then that will allow them to predict the period. And they also use some uncertainties, like what measurement or what were the reasons for the error, what was the uncertainties, the friction, the length, the circular motion, that being not like perfectly circular, and the radius. So these were all practices that we had in this section. Well, these are the science practices that we have covered in this experiment, and that is basically it. And thank you for watching. See you next time.